what they showed in some of the recent work is that you run into problems if you try to minimize the loss function that we talked about, which is trying to minimize the kind of TD error directly. And instead, you actually get something that's much more well-behaved if you incorporate the function approximation itself into the loss function. So take advantage of the fact that we know that we're changing parameters that are ultimately going to influence a linear representation of the function, and that through that linear representation of the function, that's where we're going to actually measure the loss. And so the projection with respect to the function approximator ends up showing up in the loss function, and that makes things happier.
Oh, nice. Well done. So we had successes, we had problems, and then we have successes again. That's pretty good.
Yeah, and one other thing to note on the successes side is that the current, we didn't talk about this so much, but the go-to algorithm these days is called fitted Q iteration, which is a way of mixing function approximation and Q-value learning together that, again, it has the same kinds of problems. It need not work. It need not converge. It can behave really badly. But this is something that a lot of people have gotten to work decently. So if you're trying to solve these kinds of problems, this is the go-to. GTD is not quite there yet. It's more of theoretical interest, but the hope is that these will actually come more together in the future. And there's one other topic that we spent time on that I think is worth mentioning, which is the notion of averagers.
Yes.
And the cool thing about an averager was not only were things well behaved, you got convergence with a function approximator, but it actually could be viewed as a kind of MDP itself. The function approximator could be viewed as a kind of MDP itself, which lets us get all kinds of nice properties, like that there's a unique value function that it needs to converge to. One thing we didn't talk about that's also really related to this topic is in the averager case, we had a set of anchor points. Remember that?
Yes, I do.
As the number of anchor points increases, the error in the value function approximation that you get actually goes down. And so you can actually converge over time on not only an answer, but actually the right answer, the right value function in the limit.
Right, because this was just K and N, right? Or was a lot like K and N. And that would be true for K and N as well.
Yes.
Right? If you had an infinite number of points, for example, you could actually represent the function.
So in our optional reading, we'll actually put a link to the first paper that really goes through that argument and shows that, in fact, as the amount of data increases, things like averagers, kernel methods, converge to the optimal value function, the true value function.
That's really cool. So is that everything we learned, including stuff we didn't learn?
I think that's everything we learned and a bunch of things that we didn't learn. And then I probably should also just say LSPI and just leave it at that.
I think that's right. We have to leave them to go learn something on their own. Otherwise, what would the point be?
Yes. Least squares policy iteration, which is a kind of linear function approximation where policy improvement is actually incorporated into the system itself. And it has some super nice properties, and people have gotten it to do good things. The tricky thing is always the feature set. Getting the right feature so that linear function approximation does an okay job.
Well, that's always true, isn't it?
Exactly.
I mean, it's if we could always have the right features, then the problem becomes easy.
So that's a lot to learn.
Yeah, and to have learned. What are we going to do next time, Michael?
Here, I'll give you a hint. I'm hiding the slide. We're going to talk about partially observable models.
Okay, that makes sense. That means like lots of opportunities for puns.
All right, we'll see you there then. Wouldn't want to miss that.
See, it has already begun. All right, well, bye, Michael.
See you, Charles.